This is part 3 of a 4-part series. And in this episode, we're going to talk about surfaces of revolution. So recall from the last episode, we talked about the lateral surface area of a frustum, which is a portion of a cone. And we determined that the formula for the lateral surface area of a frustum is 2 pi L. L is the slant height times the average of the radii, the radius of the top base and the radius of the bottom base. So now let's take a look at a function y equals f of x, and let's revolve that function around the graph of that function around the x-axis. What we get is a solid. Let's just say we start at some point A and we go to some other point B, and we get a solid. You've seen this before when you talked about volumes of revolution. But what I want to look at now today is the surface area around the outside of this solid. So just like we did when we were looking at volumes, what we do is we take one strip and we try and figure out what's happening with that one strip. And then we're going to add up all the strips, and then we'll take a little limit as the strips get narrower and narrower, and we have more and more and more strips. And in the limit, the sum will become an integral, and we'll have a formula for the surface area, or the lateral surface area of this three-dimensional object. So take a look at this strip, and I hope that what you see is a little frustum, right? It's not exactly a cylinder, it's really a frustum. Coloring it in so it could be a little bit more obvious to you. And we need to figure out what is the surface area of one strip. So using the formula that we have above here for the lateral surface area of a frustum, it's 2 pi. The slant height, I'm not going to call it L, I'm going to call it delta L, because remember, this is a narrow strip and we're going to let that strip become more and more and more narrow. So this is 2 pi delta L times the average of the radii. And the radii here, one radius, let's see if I could show you in another color. One radius, the green radius is on this side. The red radius is on this side, and those radii are really just the function values. So we have f of something, xi, let's say, plus f of xi plus 1. 2 pi delta L times the average of the radii. So first of all, what is delta L? We need to figure out what delta L is. Let me redraw that little tiny frustum here. This is delta L. I want my sum to become an integral, so I have to do things in terms of x and y, not this other variable L. This is delta x, and this is delta y. Do you see that little right triangle? Is that screaming Pythagorean theorem at you? Because it should be. Delta x squared plus delta y squared is equal to delta L squared. Exact same thing as a squared plus b squared equals c squared. And so delta L is the square root of delta x squared plus delta y squared. So we will sub that in for the delta L in the formula. Let me clean that up a little bit. Let me multiply this by delta x over delta x. If I keep this delta x outside of the radical sign and I move this delta x inside the radical sign, then my delta L becomes square root of delta x over delta x squared plus delta y over delta x squared with another delta x on the outside. That's actually maybe looks messier, but it's actually so much better because look at this. Delta L is now equal to the square root of 1 plus delta y over delta x squared delta x. And when we take the limit and let those strips get skinnier and skinnier and skinnier, the delta y over delta x is going to become what? The derivative, right? dy dx. So we'll be able to rewrite that as an integral. So sum up all the strips. Take the limit as delta x goes to 0. The sum becomes the integral. And what we are left with is a formula for the surface area of this entire three-dimensional thing. It will be the integral from a to b, 2 pi. I can pull the 2 pi out in front of everything. What happened to the average of the radii? Well, let's look back up at this picture here. The strips are getting thinner and thinner and thinner, and so the average of the radii, we can just call that a radius, right? It's just any one radius. So going back to the formula, we have 2 pi integral from a to b, r of xi. Now we have the square root of 1 plus dy dx squared dx. And that's our formula for the surface area of a solid of revolution. Keep that in mind. We're going to use that in episode 4.